This is Jack Jackson. In this video we're going to be looking at the concept of a vector. So we're going to be introducing vectors. So a vector, we can think of it geometrically as a directed line segment. So you see a vector right here. This purple is a directed line segment. Now the arrow on this end is not so much it's not like a ray. So sometimes we use the same notation for a ray in Geometry Sketchpad. Here's a ray, and this ray goes on forever. It goes on off screen. Now sometimes we'll refer to this as we'll have the same kind of a notation. So it'll look like this, and you'll be an arrow somewhere where it leaves the page, but it goes on forever. That is not what we're talking about here. In a vector we have, it is just a line segment, so it has a length. The arrow just indicates the direction. So you want to think of this as a displacement vector. You want to think of it as starting at the initial point and making some motion that moves you to the other endpoint. So it starts here and it moves to here. So it gives you the direction. It's going this direction. The arrow indicates which end is the initial point and which end is the terminal point. So it's that amount of displacement. So that's the basic concepts that we want to think of as a vector. So there are two main forms that we're going to have for a vector. There's a component or rectangular form, and then a magnitude and direction, or sometimes called a polar form for a vector. So let's first look at the component form. So let's look at this vector v here. And it's given by components, and this particular one is dynamic, so I can go in here and type a number. Let's make this -3, and then we'll make this 4. And so that determines the vector. Well, what do these mean? So sometimes we'll use this notation where we have these looks like less than and greater thans that will take our vector, and then we have our horizontal or x component here, and then our vertical or y component here. So of this vector v, this is the x component, or we could just call this x. Really it's delta x. It's the change in x going from the initial point to the terminal point. How far do we change horizontally? And then the y coordinate, v sub y, or just y if we want to call it that, is really delta y. It's how far we change in y. And so we can think of this vector as really actually the sum, as we'll see in a later video, of two vectors. One is going left or right, and the other one's going up or down. So this -3 that we have for our first coordinate here, our x component, this -3 says that this point is going 3 units to the left. So the first component is either left or right. If it's negative there, it's to the left. And if we put in, say, a positive number here, then the vector is going to the right. Okay, and the second number, in this case 4, is saying that we're going up 4. So this is going to the right and up. So this is the horizontal component, and there's the vertical component, and it's gone by these two, told by these two numbers here. Now another way we can think of a vector is by magnitude and a direction. Okay, and so we can specify a vector by giving its magnitude and direction. Now notice when we talk about vertical and horizontal components, or we talk about directions, there has to be some coordinate system here, that is that's in the background. So you have to have some reference point of which way is up and down and which way is left and right. But relative to that coordinate system, we have some direction. Now the magnitude is simply the length of that vector. And now if we look at this, if we know this coordinate here, which is our x, in this case right at the moment it's 5, and this is 4 in the y direction, then of course all we're really doing is just solving this right triangle to find its length for the hypotenuse. Well, that's just the Pythagorean Theorem. We've been doing this all semester. So the magnitude of vector v here is given by this kind of double absolute value sign. I've seen it also done with like a single absolute value sign as well. but I'll be using the double absolute value sign. Notice also we put a little arrow over our vectors to indicate that they are vectors. I've also seen some other notations. Some is just to use boldface for them. Boldface is a little hard to see when you're writing on the board by hand or writing on a piece of paper. So I like to use the little arrow version. So this is vector v, and the two absolute value signs, that makes the norm or the magnitude. Let me go ahead and write that. Or norm. Okay. Okay. So the magnitude or the norm of that vector is given to be, well, Pythagorean Theorem. You take the x component and square it, take the y component, square it, add them up, and then square root. In other words, you take your delta x squared plus delta y squared and square root. We've been doing this all over, time and time again. So if we call that magnitude r, we're just saying r is the square root of x squared plus y squared. Same thing we've been doing over and over and over again in terms of working with right triangles. So in this case, it's the square root of 41, or about 6.4. Now, when we talk about a direction angle, we're talking about the direction it makes with the positive part of the x-axis, or a vector that's parallel to that and pointing in the same direction. So you get a ray going to the right, directly to the right from the initial point, and then we look at this angle right here. So in this case, the angle is an acute angle. We could, well, one way to do it is a positive acute angle there. But what we do know about this angle is the tangent of that angle is going to be the y-coordinate over the x-coordinate. So that's v sub y over v sub x, or in other words, delta y over delta x. If you think about that line segment, the slope of that line segment is the tangent of that angle. So that's what we're really doing, is we're describing that. Okay? Now, the next thing that we want to notice is that it doesn't matter where you place this vector, it's the same vector. So it doesn't matter, I could put it starting at the origin. Now if I do that, this point at the terminal point actually is the point 5, 4. But of course it doesn't have to be there. It can start anywhere. What you're saying is this vector is the vector that starts at this point and goes to the right 5 and up 4, regardless of where we put it. So it's the same vector. I've not changed the vector when I moved it around. So a vector is completely independent about where it is here. It's a matter of how far we go right or left and how far we go up and down. That's thinking of it as component form. Also in terms of direction and magnitude, it's saying that we're going out a distance of square root of 41 here, as we're moving from the tail to the tip, or initial point to terminal point. And the angle that it makes with the horizontal here is going to be the angle theta, which right now is about 0.67 radians. Okay, so that's the basic idea there. Now notice we were able to take something in component form, as this one was given, and we were able to compute magnitude and direction. The magnitude was pretty straightforward. It's the square root of the x component squared plus the y component squared. And we do that. Okay, Pythagorean Theorem. And then the basic definition of we're given the x and y, or the lengths of the two legs of our triangle, and we can know that tangent of theta is that. Now, you also have to be careful that you choose the correct theta for this, because, for example, if x is negative, for example, then we're over here. For example, you can't just do inverse tangent of negative 3/4 or negative 4/3, because then that would give you an angle down here, and well, if you put it here in standard position, it would be giving an angle that's pointing down in the fourth quadrant, whereas this one actually is pointing in the third in the second quadrant. So you could think of this as this angle could be, for example, pi plus inverse tangent of 4 over negative 3. Okay, so use your knowledge of how angles work in terms of the quadrants, and the fact that tangent, we know the tangent of theta is going to be y over x, but you also have to keep track of which quadrant you're going to be in to be able to pick up the appropriate theta that will work for that. Of course, there are infinitely many thetas that will still work. I've given here the rotation that's the one between 0 and pi, if it's a second quadrant kind of an angle. Okay, but I can also rotate that around in the negative direction. I can rotate around more than once. So, as with any rotational angle, there are infinitely many coterminal angles that will be an appropriate angle for a direction angle. Okay, so there is our vector, and we can change that. Now, let me hide that, and let's look at a couple other vectors that we could do. Let's next look at one by magnitude and direction. So the green vector here, W, I give you the magnitude and the direction. So let's say the vector is going to be 5 units long, and it's going to go in a direction of, let's say 1.3 radians. Okay, and so we know that that 1.3 radians again is the angle from the horizontal. So if I were to place that at the origin here, the angle that it makes with the positive part of the x-axis is 1.3 radians, and its distance out is a distance of 5. Okay, now can we get the x and y components from this? We can compute those. Remember, we have a basic setup, is that once again, if we looked at the triangle that made up those components, then we know that the, let's call the magnitude of that r, okay, and we see that x over r is cosine of the angle theta, so x is r cosine theta, and similarly y is r sine of theta. Okay, and r being the magnitude. Okay, so if we take the magnitude times the cosine of the angle, we get the length of the x coordinate and the y component and y component here, x component here. So this is saying we're going to the right 1.34 units, and we're going up 4.82 units. So in component form, you could write it like this. Of course, that's rounded off to 2 decimal places. So again, we can specify a vector like this one, the purple one, by giving components, and then from there we can figure out magnitude and direction, or like the green one, we can specify magnitude and direction and then compute components. Probably the easiest way is the going straight from the magnitude and direction to the components, because it's really straightforward. R cosine theta is x, r sine theta is y, and those are your x and y components. Very straightforward. Going the other way, a little bit harder, because you do get to that point where you know tangent of theta is y over x. Then you have to think a little bit about what theta is going to be depending on which quadrant. Now another way we could specify a vector is just specify 2 points. So let's say, for example, okay, we start at say 0.3 or 0.3.1, and then we can go, to some place here, wherever. Okay, and so let's see if I can get it close to a whole number here. Okay, so for example, we go from 0, 3 to say 4, 11. Yeah, close. Okay, and how do we find that vector? Well, in component form, remember that the x component is the change in the x values. So if we're thinking of initial point is at A is 0, 3, and the terminal point is at 4, 11, then the delta x is 4 minus 0, or 4. We went 4 to the right. And then the change in y is 11 minus 3, or 8. So we went up 8. Okay, so we went to the right 4 and up 8. Now notice if I move this around, I'm still going to the right 4 and up 8. It's still the same vector. Even though these points are changing, the delta y and the delta x are not changing. If I move the point around at the end, now delta y and delta x are changing, so it's definitely a different vector. So there's an introduction to vectors. It turns out that vectors are very useful. Vectors have magnitude and direction. And when we talk about vectors, if we talk about something that has magnitude only, it would be called a scalar. Okay. Now a scalar, for our purposes, is just a real number. And some things, so probably one of the easiest things to explain is the difference between a scalar quantity and a vector quantity. Let's first talk about distance versus displacement. If I say I'm standing here or sitting here at my desk and I say I'm going to go 6 miles from here, well, where do I end up? Well, I know I end up 6 miles away, but where could that be? Assuming I stay on the surface of the earth, that could be anywhere on a circle centered here where I'm sitting with radius 6 miles. It could be anywhere on that circle. If I'm allowed to move in 3 dimensions, it could be anywhere on the surface of a sphere. Okay. Now, some of those may be more likely than others, but we really don't know where I am. But if I'm sitting here at my desk and I say, okay, I'm going to go 6 miles due east. Now I've given both a magnitude and a direction, so now I know exactly where I'm going to end up. Assuming you know where I start, you're going to know exactly where we end up because I've given you both a magnitude and a direction. So the magnitude and direction, that was a displacement vector, 6 miles due east. Whereas I just said a distance of 6 miles, that's a scalar quantity. Now we turn around and divide these things by time, and we get two quantities called velocity and speed. Velocity is a vector. It has a magnitude and a direction. Okay, 12 miles per hour due north. Okay, might be a velocity vector. And whereas a speed would just be the 12 miles per hour without specifying any direction. So there's a basic introduction to vectors. In subsequent videos, we're going to learn how to do operations with these vectors.